That's a good one. All right, folks. Good morning.
Morning.
It has been a hectic day so far. It's like second hour. But
so we should just do nothing.
Oh no, I've got plans for you. Anyway, don't worry, they're fun plans. I gotta remember if I think I did record.
Is that any video?
I have a short little snippet. Am I record? I am. Woohoo! Ugh. All right. So now we get into the fun stuff dealing with motion in space. You know what it's a reference to? Muppets in Space. Come on. Genius. All right. So what we're going to be looking at is a few laws by the gentleman named Johannes Kepler. We're going to be looking at a couple sample problems and then discuss weight and weightlessness. Since we are talking about space, we're going to be talking about weightlessness. So we're going to describe Kepler's laws of planetary motion. We're going to relate Newton's mathematical analysis of gravitational force to the elliptical planetary orbits proposed by Kepler and solve problems involving orbital speed and period. So you will be applying or writing down some new formulas today, okay? Anyway, I've got a couple introductory slides about who was Johannes Kepler. Well, as you see here, he did a lot of stuff, okay? Did a lot of stuff. And, I mean, he made really had the idea of the pinhole camera, discussed the refraction of within the eye, yada, yada, yada. So he was very involved in optics. So if you are an individual who wears glasses, you can really thank Kepler for this. Again, Kepler. If you want to, you can read all the stuff that he did, okay? If you really want to thank him, this one right here. He formed the basis of integral calculus. So you're welcome, says Kepler. Anyway, again, I'm not going to waste too much time just going over the history of what he's done. You can do that in your free time this weekend and give me a 5-page paper on him. Due Monday. Anyway, I'm kidding. 4 pages. Okay. Let's get to the laws and stuff, okay? Anyway, the basis of his laws are to describe the motion of planets. His first law states that each planet travels in an elliptical orbit around the sun, and that the sun is at one of the focal points. His second law states that an imaginary line drawn from the sun to any planet is going to sweep out equal areas in equal time intervals, which is going to be a huge key when it comes to the elliptical orbits of planets around the sun, because as you know, planets move farther or closer away from the sun, we have speeds changing. And his third law states that the square of a planet's orbital period, which is denoted as capital T squared, is proportional to the cube of the average distance, r cubed, between the planet and the sun. Now, keep in mind that we have already established that when we measure distance between objects, we always go from the center of the objects, okay? That point right there is going to be a key role in the calculations today, okay? Especially when we start talking about satellites and everything like that. Because typically, when you measure the distance between Earth and a satellite, you're measuring from the surface of the Earth to the satellite. But, as I just mentioned, we don't typically measure What are you shaking your head back there for? This is all I thought. But again, typically we always measure, when it comes to this type of motion, the distance between the center of objects. So not only are you going to have to, a lot of times, focus your attention on the distance between the surface of the planet and the satellite, but also add in there the radius of the Earth, or whatever planet we're talking about, and put that as a total distance when we are talking about this. And you're going to see it in one of your examples here today. So, these laws that Kepler developed were done well before Newton came out with his law of universal gravitation. But Newton took it a step further, that is Kepler's ideas and laws, and he said, yeah, they're consistent with my law, because I'm Newton. They're good with me, so that means they're okay. So the fact that Kepler's laws closely matched observations gave additional support for Newton's theory. So this is looking at Kepler's second law, which again, right there, it says an imaginary line drawn from the sun to any planet is going to sweep out equal areas in equal time intervals. So to get a vision of this, we look at a planet that is orbiting the sun. According to Kepler's second law, if the time a planet takes to travel the arc on the left, this one right here, is equal to the time the planet takes to cover the arc on the right here, then the two areas that are covered should be equal. So as you see, this planet here is closer to the sun, meaning it's going to go what in terms of speed? Faster, okay? So if you go faster, you're going to cover more area, okay? But, again, think of the area itself. It's pie-shaped, okay? So yeah, you're going to cover more area this way, but your distance this way is going to be shorter. Whereas as you get further away, the opposite's going to be true. You're going to move slower, but in terms of area, your area is going to be the same. I am going to give you a big hint. Star this slide. Starring anything means muy importante. You might just see that concept again. Okay? So let's get into formulas. Again, we saw that Kepler's third law states that the square of the period is proportional to the cube of the distance, or the radius. And what we're going to include in this formula is the constant of proportionality, which is 4 pi squared divided by g times m. So the g is going to be the gravitational constant we've already dealt with, and the m is the mass, where mass is the object being orbited. So that central figure. Again, not the object orbiting, the object being orbited. So you get a formula like that. So, this third law also leads to an equation for the period of an object in circular orbit. The speed of an object in circular orbit depends on the same factors. So, again, m in both of these is still the central object being orbited. The mass of the planet or satellite that is in orbit does not affect its speed or period. So, 3 formulas here. Period speed. All using very similar. In fact, if you look at one for period, take out that square, you're still dealing with a version of the proportionality constant.
Which one is which?
The T is period.
Okay, so what was the one on the side?
This is just stating Kepler's law, third law.
Oh, so that's not the one.
So no, typically when you are going to be calculating speed in period, you're using these two.
So we don't need it first? Or do we need to write down?
You should still write it down.
Okay.
Okay? Should still write it down. You guys like to jot that down before we get into our next thing. Yes, art of the third. Because still sticking with Kepler's third law where it talks about the cube of the radius. Now you're going to be having some decent numbers in this calculation. Decent. Do you kids still say that? Decent. Decent. Again, very important to note this. The distance between the centers of the two bodies. So memorize this table. Or don't, I don't care. Because you'll be given it. I guess you don't have to memorize it. I just love, by this time you probably don't believe anything I say anyway. You're like my kids. Not that I lie to my kids or anything like that. Okay. Let's look at a sample problem here. So we're going to be looking at the period and speed of an orbiting object. So Magellan was the first planetary spacecraft to be launched from a space shuttle. During the spacecraft's fifth orbit around Venus, Magellan traveled at a mean altitude of 361 kilometers. If the orbit had been circular, what would Magellan's period and speed have been? Now again, in the previous slide, it states that these calculations are for a circular orbit. Whereas we know that, planetary is elliptical. Okay? These are circular. And we have satellite in this situation. So, what do we know? We know that the distance between Magellan and, I forgot what planet it was, Venus was 361 kilometers. We need to make sure that our distance is presented in meters for your calculations. So we convert that 3.61 times 10 to the 5th meters. And really, that's all we need to know. Because the other stuff is going to be, relatively constant, except for m. You're going to have to be given that or look it up. Mostly you'll be given it. Okay? So we need to choose an equation, a situation, since we have to determine both period and speed. We're going to use both of those formulas. So the table that was in your notes is the table it's referring to, okay? Because we need to know the value of the masses, the mass of Venus, as well as the radius of Venus. The radius of Venus in that table is 6.05 times 10 to the 6th meters, and the mass is given here as 4.87 times 10 to the 24th kilograms. So once you have the radius, the mass of the planet, along with whatever other information you were given in the problem, you can then go ahead and start beginning your calculations. But the final step before doing so is an initial calculation. And that is taking the radius of the planet in question, this time Venus, and add it to the distance that Magellan is from its surface. Again, going back to the point that it's all based off the center part of the bodies. So we get our total distance from the center of Venus to Magellan. Now we can finally start calculating our two items. So to calculate period. Again, we're going to be using some very fun numbers in here. All right. So again, you take the cube of your distance divided by the gravitational constant, and multiply the gravitational constant by the mass of Venus, and you'll get your period. Reminder that when we use the term period, we're talking about a time frame. Your time frame will be in seconds. As you notice in the problem itself, there is no unit for seconds. You need to remember that. It is in seconds. Since we found the period, we can then go ahead and calculate the speed. And so, again, taking the same values of the universal gravitational constant and the mass of Venus divided by simply the overall distance between the two bodies, we get a speed of 7.12 times 10 to the third meters per second. So ultimately, these aren't terribly difficult setup situations. It's the fact that the numbers are so large in terms of positive and magnitude or negative magnitudes. Okay, so just be very careful when it comes to calculating these. Now we're going to come back and do some additional examples. Okay, I want to finish the notes before we get to those. Okay. If you wanted to, you could determine what the overall time it takes to create one orbit by taking the period and converting it to minutes. So it takes about 94 minutes to complete one orbit of Venus. All right. So last topic that we mentioned in the objectives was weight and weightlessness. Okay. Whenever you hear about somebody being in space, they say, "Oh, I'm weightless." Well, it's not really weightlessness. Okay. So think about this. You're in an elevator. I'm sure you've, been in an elevator, right? When the elevator is at rest, the magnitude of the normal force acting on you is going to equal your weight. That's going from way back in the school year. If the elevator were to accelerate downward at 9.81 meters per second squared, you and the elevator would both be in free fall. You have the same weight, but there is no normal force acting on you. So this is what we call apparent weightlessness. You have not magically lost your weight. There's just not another force counteracting gravity at that moment. And so this is what astronauts that are in space are experiencing. Okay? They don't magically lose their weight. Now, I always like to show this video. It's a few years old now. About a certain ride. And the certain ride is known as the what? You know what it is.
Tower of Terror.
The Tower of Terror, located where?
Disney.
Disney, what park?
I haven't been there in a while.
Oh my gosh, who?
Hollywood.
Hollywood Studios. Very good. So, anyway, have any of you ridden this ride? Okay. So anyway, it is a elevator ride that is not like any other elevator ride. It actually, you go up and down a few scenes after you enter this cart, but then it does what elevators don't do. It comes out and travels autonomously by itself, meaning that's what autonomous means. And it goes throughout the scenes, and all of a sudden you enter the front of the building that you're in. Next thing you know, you enter a ride sequence. And there are multiple ride sequences of this attraction. So it changes almost every time. You either get shot up, shot down, mixture of both. But what's different about this compared to other elevators is other elevators, you are gently lowered down. Okay? Even if you were in free fall in an elevator, you're still accelerating at 9.81 meters per second squared. Disney, being Disney, they upped it a notch. They actually have motors that pull you down faster than gravity, which is amazing. And so instead of watching this video, we're going to watch this video of my. That's unavailable anyway. Again, this is a few years ago, where my family were at Disney. We rode this ride, and they give you a video of this. And so,
1939. The Hollywood Tower Hotel was a star, a beacon for the show business elite. Until 5 people
That's not
stepped
me.
through the door of an elevator and into a
There's me.
nightmare. Now that door has opened once again.
You see my daughter, my wife. She's like putting on for dear life. Anyway, it's an awesome ride. But it just takes that whole idea of apparent weightlessness to another step. But I want to get back to calculating, because this is what you're going to need for your homework. Go ahead and open up your textbooks. To page 251. All right, page 251. And let's look at number 1. Okay, actually, I guess I ought to open up my book too. 251. Making sure. See if anybody was. That's a phone. All right. Number 1. On page 251 says, find the orbital speed and period that the Magellan satellite from sample problem D, so the one we just did, would have at the same mean altitude above Earth, Jupiter, and Earth's moon. Let's just do Earth, okay? Because it's all the same process. All right. So we are doing Earth. The distance, again, same mean altitude from the previous problem. So again, I'm just doing R1 right now. It's 3.61 times 10 to the 5th. Again, that's not including the radius of Earth. That's in meters. The mass of Earth, as we see in a table on the previous page, on page 250, the mass is 5.97 times 10 to the 24th kilograms. And the radius of Earth is 6.38 times 10 to the 6th meters. All right. So before we do anything, we got to add these two sums together. So R1 plus RE, when you add those together, you get 6.74 times 10 to the 6th meters. So let's calculate period first. Okay, so period is equal to 2 pi multiplied by the square of our overall distance, which is also going to be cubed, 6.74 times 10 to the 6th cubed. That's meter. It's an M. Divided by gravitational constant, 6.673 times 10 to the negative 11th. And for ease of space, I'm not going to include the units because I will run out of space. And that's multiplied by the mass of Earth, 5.97 times 10 to the 24th kilogram. All right. So we got everything in here. Again, it's 2 pi times the square root of the cube of 6.74 times 10 to the 6 meters divided by the product of 6.63 times 10 to the negative 11th and 5.97 times 10 to the 24th. I want you to plug that into your calculator just to verify that you are calculating it correctly. So when you plug in your calculator, you should get 5.51 times 10 to the 3rd seconds. Is that what you're getting at there? Just double checking. Excellent. So that's your period. Next, let's calculate the speed. So again, you're going to take the square root. This time you're going to have your gravitational constant, 6.673 times 10 to the negative 11th. Now I'm just going to take that and then multiply it by the result of taking our mass, 5.97 times 10 to the 24th divided by 6.74 times 10 to the 6th meters, which again is our distance. So plug that in just to verify. So you should get 7.69 times 10 to the 3rd meters per second. And that would be the speed of Magellan at Earth at that distance from the surface. Questions? Again, if the problems in your homework don't give you the correct or the proper planetary data, use page 250. For your homework, you're going to have something you cross out. So you are going to cross out number 5 and number 7. Number 5 and number 7 cross out. So you'll do the remaining 5 questions. That's right then. Oh, also cross out number 2. Apparently I can't read numbers. Cross out number 2 as well. 2, 5, 7.